So I have it here from Thursday of last week, long time ago. What are we looking at? Yeah, so here I wanted you to kind of pay attention again or remember the concept of differential. So we looked at, if you remember, we looked at the simple scalar valued function of a scalar, very simple, and then we kind of used the definition of derivative, if you remember. And I tried to convince you that the change in dependent variable y is to the first order approximation, like a linear approximation, would be equal to the differential. And the differential dy, so it is different from delta y, dy is a function of delta x, and it is a linear function. And it also has some connection to a specific point x naught. This is what we were. Do you remember why I'm doing this? Why did I start with this simple bringing this up, recalling that? Go back to your notes. That will help you kind of warm up a little bit. Yeah, so my intention now is to define gradient. It looks to me that a lot of students, they have learned gradient in the context of Cartesian coordinates. But we want to kind of define gradients in the more general sense, and then we go from the general definition to defining it or to write it in different coordinate systems. So what I wanted to do was to define gradient, which I haven't done so far. So that's kind of where we are going to start. So I start over in the new clean sheets by first telling you what I want to do today, I guess. So this is too thick. So I want to define a gradient independent of a coordinate system, just a concept. And then divergence, this is what kind of my plan was to do last time, but I didn't get to do it. And afterwards, I actually want to introduce coordinate systems. And I hope that today we can talk about Cartesian coordinates. For some reason, this is comes very large. It's very noisy kind of my pen today. Gradient. Strange. Okay. So for that, let's kind of start where we left off last time, and let's consider this time my pen is behaving a little bit strange. I quickly changed the battery. That's sometimes I don't know if any of you guys have experience with this, but that's the only thing which I have seen could be the reason for this. So we want to consider a scalar valued function of points. Try to formulate that if we consider f, it is mapping what to what. So don't wait on me while I'm trying to change this battery here. Hopefully it's going to fix the situation. Yes, I don't know why battery has something to do with the thickness, but it's beyond me. So let's consider so a scalar valued function of points. F and I think last time I asked you for some examples, so I tried to make like a small sketch here. Like imagine that we have an object and this is mapping and here is the real values, and always we look at a function as a mapping, right? This is f mapping every point on the object to a real value on the real value line. I'm showing this with a line. What example did I at the end tell you about? Density. Like that's kind of a classic example of that. So now we do exactly what we did before for the scalar valued function of a scalar dy. So if I write here delta f, how did we write it? We said, okay, delta f would be f evaluated at, let's call this x naught plus a small change in independent variable x, and just exactly like before. The only difference is that now this is a function of points. Before we just had x without any line at the bottom. So just like before, now I don't go through the lengths of explaining what. We will have differential plus higher order terms. Maybe I should do this. Okay. And differential, is it a function of what? Is it a function? Yes. What kind of a function?
Of delta x.
A function of delta x. What kind of a function is it? And it is evaluated around x0. It's a linear function. So before, when I was reviewing linear functions, I had a purpose because it's very important for us. So it's a linear function of what kind of variable it has. Is it a scalar valued function of a scalar or a vector? Because delta x, remember, it's a vector, right? So if I want to write df, it's mapping what to what? It's going from the vector space to set of real numbers. And what did we learn about? This is a couple of lectures ago, and I think a lot of you probably thought, you know, this looks so obvious. We did some examples about linear functions, linear scalar valued functions of vectors. What did we learn about them? Does anyone, by any chance, remember? We said we can write them as what? Their actions on the vector.
That's the sum of the independent pieces?
No. You want to look back. If you have your notes all in one place, try to look back when I was teaching you about linear functions. I told you something about them, a property they have. A theorem. It was a theorem. I didn't give you any proof. I just said.
Back
Exactly. So if you have a linear scalar valued function of a vector, before we saw that you can write the action as a dot product. So you can, instead of writing the function like that, you can express it as a dot product. So this is a function of delta x. You all agree with me. So the action on the delta x can be represented by a dot product. Dot product of two vectors. One is delta x, the other one is a vector. For now, I call it, and this one should be somewhat evaluated at x0. Compare this with the scalar valued function of a scalar. That is kind of where we have derivative. You know, the differential of a function is just derivative times delta x, right? Now we are looking at the scalar valued function of variable. Instead of having that simple multiplication, you have an inner product, and here we have two vectors multiplied. So what do you call this one? This vector now? If you have ever seen this before.
The differential operator?
Yes and no. There is a differential operator in the symbol, but what is it? The quantity. It's a gradient. That's what I was looking for. This is the very definition of gradient without having any kind of connection to any coordinate system. I know that you may not be used to that because you have always seen gradient partial derivative with respect to x, I plus da 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 da. But I want to tell you that this is actually the definition of gradient. And once you know that, you can actually translate it in different coordinate systems. So this is the definition of gradient of f evaluated at, and that's I think this is what you were talking about. So that's why I said yes and no, because I knew that you are thinking correctly. So one thing very important, I write this in black, and I should remember to switch back to blue, because looking at the notes, I'm switching back and forth between blue and black. What kind of object it is? That's super important.
Vector.
It's a vector. Remember, the function was a scalar valued, but its gradient became a vector. So it goes kind of one order high up, right? So I just write that the gradient of the scalar valued, because this is so important. Function f is a vector. Okay, so I've been able to define gradient for you without even having told you anything about coordinate systems. Now, you can kind of see where it goes. Now, I just show you what happens if we have a function which is mapping vectors to vectors. So to have a vector valued function of a vector. So I want to consider now a function. I call it v, like before. And this function is mapping points into vector space. What do we call these kinds of functions in engineering? Think about it. It's a function where, let's say, you have a body And at every point, you have a vector defined. It's continuous. Everything we are doing here is in the realm of continuum mechanics. But maybe it's the best to ask you, do you know an example like that? So for a scalar valued function, density, Prabhas favorite was temperature, right? For vector valued function of position, what is one example?
Velocity field.
For example, it's a velocity field. And pay attention that your friend used the word field. That's important. So we normally call them like field. Displacement field, you have heard this before, right? From your looks, it's hard to say. Velocity field, you have seen that. So this is kind of those kinds of variables. I call it like in general vector field, but as engineers, we kind of like to have some more, and I do exactly what I did before. I want to get the gradient of this function. That's where I'm going. What do? I look at the change in this function. I write it exactly like before, just compare it like just like before. It's the change. I define it by the change in the value of the function when you are looking at a point x naught plus delta x and point x naught. And I guess by now, hopefully, everyone can quickly see that this becomes the differential, that's the first order approximation, plus higher order terms, which in this class we don't really consider, right? Now, and you know that those higher order terms, they go faster towards zero when delta x becomes tinier and tinier. So I don't keep repeating and writing those down. Now, you can kind of see where I'm going. I want to define gradient, okay? And what is gradient? It's, let's look at before. What was the gradient? It kind of connects the differential to delta x. So how would it be here? So here is the differential. In this case, it's a vector valued function. You all agree it's a function, right? It's a function. Differential itself is a function. And delta x. Here you have a vector, and on the other side you have a vector. What comes in between is gradient. This is the definition. What kind of object is it? It's a tensor. Didn't we define tensor as a linear mapping of a vector to vector? So this is just a tensor. So I don't make the same kind of tricks before. So I start just by writing that this will be the gradient. This is not a dot product. This is the action of a tensor on a vector. Both sides are now vectors, right? So what do you see? Before, the gradient of a scalar valued function turned out to be a vector, right? Now, what statement are you guys going to write without my help? What did you learn here?
I have a question. Mm-hmm. I was tempted to see the first gradient we define as a divergence. Because it's
divergence?
Yes, because it's dotting on a vector into scalar, making it scalar.
This is a common kind of mistake. Yeah. Divergence is a number for it. So and the dot comes between the operator, which you have seen in elementary courses, and the function. This dot comes between the vector and the changes in independent variable. So this del operator is, for centuries, have misled students. So towards the end of this lecture, I'll talk about it, and you kind of see how it is related. But divergence is del operator dot, but this dot is between the vector and the delta x. I didn't even need to use this del operator. This is just the name I gave it. The same way as my name is Parisa, I could have named something else here, right? I just chose the del operator because everyone else does that, right? Because this is the convention that we have used. But it's not necessary. Did I answer your question? We'll get to divergence. If you never heard of it, don't worry. It's just a couple of minutes from now. So what a statement did you write for yourself? Comparable to the black statement that I wrote there. What do you write now? What did we learn? The gradient of a vector-valued function is a tensor. These are important to remember. So let's just write it. So we are kind of going one order up in gradient, if you may. And now that we know what gradient is, we are ready to define divergence, which your friend, even before I talked about it, right? So how do we define divergence without having talked about coordinate systems? So this is kind of what my goal is. How would you actually define divergence?
It moves whatever it's acting on down one level. So like the divergence of a vector is a scalar, the divergence of a second order tensor is a vector.
This is correct. How would you define it? First of all, let me ask you this question. Is it defined divergence of a scalar valued function? Actually, I should have said that. Is it defined at all? No. Right. You talked about dot product. So if you don't know what we are talking about, don't worry about it. But even the dot product is not even defined for something which is not a vector valued function. So actually it's quite simple. So the divergence of a vector valued function is just the trace of gradient. So once we know the gradient, and the gradient, remember, is a tensor. If you take the trace of that tensor, that's the divergence. And going back to the point that your friend made, I forgot your name for whatever reason now, Tom. So what type of quantity it is, divergence? Is it a vector, a scalar, a tensor? It's a scalar. So from vector, we are going to a scalar. So actually here we are going down one order. You can think about it this way. Now, I also define the divergence of a tensor Remember, this is a definition. Later on, when we want to calculate it, we look at the coordinate system. So don't worry if it looks a little bit abstract to you. It is. So divergence of a tensor is what kind of an object do you expect? A vector field. Is that vector field such that for A, which is a constant vector field, this is the definition. Don't worry too much about it. In coordinate systems, you can see how it will translate. But that's how it is being defined. And why are we talking about divergence? Does anyone remember why you have seen divergence before? There is a theorem which is turns out to be very important in different branches of physics. And for formulating that theorem, it's very useful to have divergence. And it is called divergence theorem. So let's remind ourselves what this theorem was about. Oh, that's interesting. Okay, I cannot get it. Oh, so, let's see. Since this is very important, so I make a sketch. So consider a region in a space. This is maximum 3D for us. So R, this is R. A region of a space. And this has a boundary, so that can be a line or can be a surface. I show it by delta R. And then the outward unit vector, or it's called normal vector, of course we don't show the proof or anything like that. I just want to show you what the theorem says. So considering phi being a scalar valued function, like function of points, this is more like a field, right? And v a vector valued and T a tensor value. So what does the theorem says? The theorem says that the integral of phi times n dA, which is the area element of delta R, is the same as taking the integral over the volume of the gradient of the scalar valued field times dV. This is the volume element. So sometimes you see that people use like 2 or 3 integrals. It's the same thing. So this theorem is important because it kind of relates the things at the boundary to the interior of an object. You will see later that this is a very useful theorem. For vector valued functions, the form is similar. So far we didn't see divergence. So if you look at the vector valued, maybe I switch to another page. Let me write it and then we talk about it a little bit. So here you use the divergence of V dV. And I don't have this columns today. And if you look at the tensor value, there is a variation of the last one. So in all of them, what we see again is that you are equating an integral taken over a boundary to an integral which is taken over the interior. So that's kind of the power of this theorem. You relate things which are inside an object to its boundary. This is quite amazing, right? Another thing is that so far, again, we have never introduced any kind of coordinate system. So this is good no matter what coordinate system we are going to use. Any questions so far? Yes.
This also dependent on whether you're applying or
In which sense?
for the definition of the applying, because it's not exactly the coordinate frame, but it's like
It has, I haven't yet talked about any coordinates, so these are as general as it gets. So then depending on the frame that you are going to use, you can use any kind of framework that you need. So far I haven't told you anything, but they all hold no matter what. So, and this is kind of the difference between how the material is being presented in the class and in the book. The book starts with Cartesian and then kind of gives you just formulas for polar. What I'm trying to do is to give you the general formulations and then kind of a specific formulation, how it translates into Cartesian and polar. And that's what we are going to do throughout the semester. I give you the general and then how it would look like in Cartesian, how it would look like in polar. And we do two-dimensional, so you are not going to see spherical or anything like that, Mustafa.
So, Professor, what do you mean here by a region? So, when you say region, I thought it was like research is a volume. But you said that the region has an area component and
Oh, so the region, I tried to make a sketch, it's not too good, but it could be any region that you are considering in a space. It can be even imaginary, so you can just consider some limits. But let's imagine like an object, or imagine like, I mean, in this class, it's pretty much an object, like whatever is you are studying its deformation. But for example, in fluid mechanics, you may consider just some cross section, and what you are looking at is really flux, going through that. So that's what I mean by region. So if it is 3D, it's the volume, right? And then delta R, the boundary is two-dimensional. But it could be 2D, and then the object is 2D, and then the boundary is just a line which goes around it. Right? Did I answer your question? Okay. So let's now start with coordinate systems. Good news, this is the last part of the mathematical preliminaries. Just like you, I'm patiently waiting for us to kind of go through all these basic preliminaries and start talking about the mechanics. Coordinate systems. So I start with just asking you what coordinate systems are. How would you define a coordinate system?
the reference frames that will be defined by everybody who can say
Reference frame. What is a reference frame? A coordinate system, right? It doesn't have to be uniform. So you choose your coordinate system depending on your object, how your object looks like, or what are you studying. You all know what it is, but I'll present it in a way that it would help me derive the equations. But the definition, the real definition from the advanced geometry is really similar to how would you define navigation tools. So a coordinate system is pretty much a navigation tool. And in which sense? Imagine, like, now I want to give you some physical sense, which will be hard, you'll see in a moment. If you are looking at a map, I know most of you have not looked at a map, Probably never. Like, let me look at you. Probably none of you has seen a map in your life before, but you have seen in movies, right? Have you seen in movies some maps? It's like, I feel like, in 10 years, people will not know what a real pencil looks like. And it makes me very sad, because it's like when your parents were talking about some cassettes or some things that you didn't know about, and now you know about some things that the little kids are not going to know about. And it's a strange feeling. So anyway, to cheer you up a little bit, imagine a map, right? What is a map? You are looking at a point on a map. You have two coordinates. Let's not call them coordinates, I haven't defined that yet. But you have like an x, y. These are both real numbers, positive, possibly. And this is kind of, now it would be hard for me, but this is like the planet Earth. This is not a ball. And like in the old times, if you bought a map, you got a planner, kind of a picture of a part on the face of the Earth. And this mapping basically takes any point and then it brings it to this planar surface. So it is really a mapping, as you can see. So this function that in a moment I'm going to define of any point, this is taking, let's say this is a subset of the Earth U. This is bringing this and mapping it to 2 points, basically. Right? You look at one point here and you read some values, and then you find wherever you want to go. So basically coordinate systems, you can think about them as navigation tools. And more importantly, think about them as really mapping. They are mapping some points from your object into, let's say, in this case, just a piece of paper, right? And then what you are going to get are, for example, in 2D, what are you going to get? You are going to get C1 and 2 This is in 2D. So they are mapping an object into, in this case, just a map, really. And then you get a number of scalars, and those scalars are coordinates. This should be very tangible for all of you. So now that we know what coordinates are, we can define a coordinate system as a procedure which gives us coordinates. So I gave you all this story to say that. So coordinates are these scalar values that you get in a, let's say, piece of paper in a map that tells you which kind of, it's the mapping of a point from the Earth, from an object, from wherever in that particular frame. So it's a procedure. You need to define a few things, as you will see, to get there. And that's what we are going to do for both Cartesian and polar coordinates. So a coordinate system is a process or a procedure which gives you coordinates. And this mapping, this is called coordinate function or coordinate map. So this is kind of, I don't know why today everything is, it's a coordinate map or the coordinate function, basically. So now I've told you everything I wanted to tell you to introduce coordinate systems. We can look at an example. Our example will be Cartesian coordinate system. So I changed the page. I lost one page, remember? So I need to copy one more. So our example is, so how do we build coordinates in Cartesian coordinate system? Example, so let's consider (2D or 3D Euclidean pointer space and see how would we define a coordinate system. The first step is to choose a point arbitrarily. So we choose a point O which belongs to this Euclidean coordinate system arbitrarily. And since we know that this is an Euclidean pointer space, we can also choose a base. And we choose an orthonormal basis. So when I say procedure, that's what I mean. You need to have a few things to get a coordinate properly defined. So with the steps. Choose an orthonormal basis. And then we need to define coordinates. So to define coordinates, I forgot to draw the point O. I have the point O. I take some other point X, and this is what I want to define. And we learned that in an Euclidean pointer space, you have 2 points. You can have a line. We learned that you can also have a vector space to define a vector which goes from O to X. So I define the coordinates as follows. So each coordinate map, which will be a function of X, would be the projection of this vector on the orthonormal basis. So the vector is we learned that if you have 2 points, the vector in between would be the difference, point difference between them. And I just multiply this by inner product with the unit vector. So what kind of object do I get? It's a scalar. Okay. So the reason I'm going very systematically because it looks very simple in Cartesian, but when you go to polar, things are not as obvious. So we kind of go systematically, and then in polar, we follow pretty much the same thing, and it would be much easier to follow, see where things are coming from. So if we consider now 2D, so two-dimensional space, because it would be hard for me to draw things in 3D. So try to write the components. So if we take, again, I have to do exactly what I said I would do. I take one point arbitrarily, and this is the origin. You have seen this in other contexts before. I have to decide on an orthonormal basis. In this case, I will only have 2, and I take one point x0, and then what would be the coordinates? The way I have defined it up there. So I have 1, stylus today is doing strange things. So that's one occasion that you wish for not having the technology, because pencil never fails, so chalk is always the same. But today, for some reason, so these are the coordinates. We all know that. Something that we need to define is the concept of coordinate lines. Too bad. We need to have, I have to draw this again. So for Cartesian, it looks very similar, very simple. So let me write the definition, and then I'll ask you to draw them. So I need to copy again these 2 points and this vector and my basis. So coordinate lines are defined as follows. So L1 is the collection of points whose first coordinate, according to the definition I just wrote earlier, would be equal to the first coordinate of point x0 plus s and its second coordinate is equal to the second coordinate of x0, and s Can be any number. And then L2, there is a reason I introduce these. So you should be patient. You will see later why we need to go through these. Draw them. Draw these two lines. You have the definition. You have seen all the symbols before. So I defined for you how you would get the coordinates of every point. It's kind of in the previous illustration. And now these are the definition of these two lines. Which we call coordinate lines. Read those definitions to the notation and translate it immediately. Yeah, I should save the correct answer. Four and a half right answers. Thank you for your last Late in the afternoon, I mean, I expect too much, right? It's just that my style is not to just write. This class makes it a little bit hard to interact, and I just look for opportunities. So don't worry about it if you don't see. Look back at the definition. I know you all know Cartesian coordinate system, but I want you to look at things with fresh eyes. So the definition is that if you have a point, you connect it to the arbitrarily chosen O, and then you dot product, you calculate the dot product with the unit vectors in the basis that you chose. Basically, that's what it says. So if you look here, imagine this, you had never seen Cartesian coordinate system before. You came from some other planet here, right? You would take x naught O, and if you take the dot product with E1, you get a number which is kind of that number which gives you, that's a number, it's not a vector, but it gives you the projection of this vector in the horizontal direction, right? So that's a number. I cannot emphasize this. This is not a vector. And this is that number. If you dot product with a unit vector, you get the projection. It's a number. So now, let's read L1. It looks very mathematical, but it's actually something not too complicated. It says all the points whose first coordinate system coordinate is equal to the coordinate of x naught plus minus some number, right? And then the second coordinate has to be equal to the second coordinate of x naught. This is a horizontal line which passes through x naught. It's important. It passes through x naught. It's not going through O, right? Because that's kind of a, this is, every point you take on this line, it's the second coordinate. Now my line was a little bit strange. The second coordinate will be equal to the second coordinate of x naught, and the first coordinate is the first coordinate plus minus any number. Does it make sense? It's a mathematical, so that's the problem. A lot of very simple things, when the language is different, it's like when you start to learn Spanish or some language you don't know. It's the same concept, but it's a different language, how it is being expressed. And it's this line. It's important that it passes through x naught, right? And of course now I think, hopefully that you can see that this will be L2. Now for Cartesian coordinate system, these lines are very obvious. You will see in polar coordinate system, they are not really lines. They can be a curve. In a spherical also, they can be curvilinears. They don't even have to be lines. But they are important conceptually, and you will see soon why. Okay, now there is one pair of them which are special, and they go through O. And what do we call them? Axes. So if you have these lines going through O, of course those are axes. I saw that some of you kind of drew them through the axis. Okay, now what we want to do, we want to go towards calculating the gradient in different coordinate systems. So I again start with simpler functions, and then we go to vector valued functions. So let's first consider the coordinate function itself. Okay, so we just learned that we have this mapping which gives us the coordinates, and it's basically a function of x. What kind of a function? The scalar. We saw that what you get are just numbers. So a scalar valued function of points. What I want to see is what would be the gradient of this function. What kind of object do you expect then? A vector. Exactly. This should be automatic. When you see a gradient, look to see the gradient of what, and then try to convince yourself that if it is a vector or a tensor. So, like before, we go through the definition. So, starting from differential, I've written this for you a few times today, so I go fast. So just write the differential so far general. From here on, this is in Cartesian. We're talking about this coordinate system. So now in Cartesian coordinates, how did I define these coordinates? So I said, okay, if you have anything, you take the vector from O, you dot product it with the unit vector, right? So I do exactly that. And you can see that some of the terms will cancel out, and this will be just that. And we learned that the differential is the gradient. That's what we are looking for. This is what we learned earlier for a scalar valued function. So if you look at these two, you see that the gradient of the coordinate function is equal to the unit vector, but this is only good for Cartesian coordinates. So if I want to make sure I can move up, try to think how these gradients, what is the relationship between them and coordinate lines? The way we defined the coordinate lines, how was it? One coordinate was kept constant, the other would vary, and the other was kept constant, the other coordinate would vary. Now, how do you think the relationship is between this gradient and the coordinate lines? I mean, you see it in front of you. The gradient of the coordinate is equal to the unit vector. But it's also important to see that, so if I want to draw the gradients here, basically they are exactly equal to the unit vectors. We just saw them, right? The first one is equal to E1, E hat 1, the second one is equal to E hat 2. So but these are at point x0. And it's important, just like, you know, you all know that the derivative is tangent to a curve. And if you look at the definition of L1 and L2, you see that this gradient is kind of tangent to the coordinate lines. It shows the slope. It's I don't know how else to see. You all see that it's a kind of tangent to the coordinate lines. Now, tangent doesn't mean much here because everything is horizontal and vertical, so it's very simple. But you will see that in polar coordinates, this is important. Are we running out of time? Let me tell you one more thing. So, because we already have this, it's important to realize that the gradient of the coordinates, they form an orthonormal basis. So, for Cartesian coordinates, because they're equal to the basically basis vectors, so another thing is that these are constant. So because we found out that the gradient is equal to the unit vector, the gradients are constant.